Okay, so this is a walkthrough of discussion 13. We're going to be doing some stuff with graphs. So first we'll start out with just representation. How do you represent these things in code? Then we'll go on to some more algorithm kind of stuff. So traversals, including DFS, BFS, and then we'll talk about pre-order versus post-order, topological sorting, and then we'll finish with Dijkstra's algorithm. And then a little I guess like trivia, not trivia, some questions on it. Okay, let's first start with the representation. So a good representation, or sorry, a valid representation is something that, it contains all necessary information so that we can reproduce, whatever thing we're trying to represent. In this case, this graph. So this is one representation of the graph, like a visual, right? So you have circles denoting nodes, and then these directed arrows, directed in this case because it's a directed graph, but you can also have undirected graphs. And then directed arrows connecting the different nodes. So that's a visual one. Let's talk about the two ones we use in our programs. So the first one is an adjacency list. So if we were to write this like in code, it would be some instance variable, and it would have the type something like map from node. I'm assuming that there's like a node class for the graph, like an inner class, kind of like how linked lists have an inner node class. So from node to a list of nodes. Okay. Yeah, and maybe it's like called something like adjacency list, whatever you want to call it. Okay, so let's write the adjacency list for this this graph. So I'll denote that it's a map, kind of like what Python does with the curly braces, and A will map to, and a list. I'll use square brackets like Python does. So A has three neighbors. It has B, E, and F, and that's because those are the ones directly connected with an edge. And note that even if the graph was undirected, you could still use an adjacency list, and you will see an adjacency matrix as well. So it's pretty easy to denote whether they're directed or undirected. That's like fine. The one thing that might be a little bit tricky is like if the edges had labels. So if it was something like a number or maybe like a string, I don't know what that would be. Like, yeah, I don't really know what a string. Maybe like maybe the nodes represent like states, and then the string represents like an action you can do to get from that state to a different state. So maybe this would be like press on the gas pedal or something like that. If this is like some sort of graph of like state objects or states of like a car, for whatever reason, if you're doing that. Yeah, so this doesn't naturally, at least I don't think it really naturally lends itself to labeled edges. You can probably modify this part, right? So maybe it's like a modified node to be not only the node, B, but also what's the label. So maybe you make like an auxiliary object, like make an edge, or make like a labeled edge class. But that's out of the scope. So that's just if you were curious, because we'll get into labeled stuff down here, right? Because with Dijkstra you need labeled edges with numbers. Okay, so yes, A has three adjacent nodes, right? B, F, and E, and the order of them doesn't matter. So I'm just going to put them in alphabetical order. So B comes first, and then E comes next, and then finally F. Okay, let's move on to the next one. B is adjacent to D. So that's just one thing, right? Let me get rid of the arrows, or these circles. B is only adjacent to D, so its list will just have D in it. Okay, C is adjacent to nothing. There's no outgoing edge from C. There is an incoming edge, but in our representation, we're not going to denote the incoming edge. So in this case, this edge from D to C won't know about it, but D will know about it because it's outgoing from D. So we're still keeping enough information here. Okay, so C maps to nothing. So you could, in your code, maybe you have like a null here or something like that, but I think it's much easier, instead of having null things, to have like I think what some people call is like a smart null or a smart zero. So in this case, an empty list. it makes the algorithms a little bit easier. Like you wouldn't have to deal with like a edge case where you have a null as like the list here in the adjacency list. So it's just a little bit easier. Okay, so that's C. Let's look at D now. D has two neighbors, C and E. Yeah, so C and E. Again, I'm going to just put them in alphabetical order, but the order does not matter at all. After D, we have E, which is adjacent to nothing. So I'm going to, again, use an empty list. Oops. Okay, and then F, which is only adjacent to E. And that's actually the last one. So that closes the map. And that's it for this graph in adjacency list representation. And you can convince yourself that this is a fine representation because just given the adjacency list, this map here, you could easily reconstruct the graph. Maybe it wouldn't look exactly like this in terms of like the B being above the F and to the left of the C and whatnot. But that part doesn't matter anyways, right? Even if I like move this B node to be like a little bit like here, it's still the same graph as long as the nodes and the edges are the same. That's all that matters. Like if I move around things like up a little bit or down, that doesn't matter at all. Okay. So yeah, just given this information on the left, you would be able to draw the graph. And it might look exactly like this, might not look exactly like that, but it'll contain the same information. Okay, the next one is the adjacency matrix, which is pretty similar. So you'll have to somehow convert the node objects to integers. So one really easy way of doing that is you keep like a counter of how many nodes you have, right? So maybe you have some instance variable n, and every time somebody adds a node, you increase n by 1. And the number you give that node, the new node, is the new value of n. So like in this case, let's say first we have the node A. So that would be like our 0th node, right? And then our node B comes along, so we'll give that the number 1, and then C 2, D 3, and so on. So E would be 4, F would be 5. And we'll just use this numbering scheme for the adjacency matrix, but it could have easily been a different permutation. Like it could have been A is 5 and C is 2, or sorry, C is already 2. C could be like 1. It doesn't matter. As long as it's like, they're all unique. That's the one thing that matters. And that they're increasing like this, like from 0 to 5. And that's because these numbers are going to serve as indices in our, in a matrix that we'll make. So you could either, if it was, and this is when it comes to, or there's like a choice you have. You could either make it like, if you're never going to add nodes to this graph, like apart from like the initial, like the constructor, if you're never going to add nodes, then you can use an array. So then you can have like, and we'll see, I'm going to use Boolean here. We'll see why. So then you can have a Boolean, not array, matrix. Let's call it adjacency mat. So adjacency matrix. Or if, people could add add nodes, delete nodes, and kind of modify it, then instead of an array, you might want to use an array list. So it would have basically the same runtime. It's just using an array list because it's dynamic in size, right? Okay, but let's just go for the array for now. Okay, and so we're gonna have a 6 by 6 square. So if I divide these into 3s, okay. Okay, and remember we labeled them all. Sorry, we labeled all the nodes with an index. So let me label the columns here. So that's A, B, C, D, E, F. A, B, C, D, E, F. And, okay, so why is it Boolean? The Boolean denotes whether that edge exists. What I mean by that is, like, let's say you wanted to know, is there an edge from A to B? Then the way you would do that is you would do something like this. You would index into it. First with the from edge. So I'll put from here. And then like the to edge. So if I wanted to know if there's an edge from A to B, then you would index it like that. And, instead of actually using the node A, you would use whatever number it corresponds to. In this case, A corresponds to 0, and B corresponds to 1. And in this case, that edge does exist, right? There is an edge from A to B. So that should be true. And that'll be true for all of the ones, right? So there's an edge from A to B, A to E, and A to F. There's not an edge from A to A. That would look something like this, like a self edge, or maybe a little cleaner. That would look something like that, kind of loops to itself. Usually we don't really have these in like the graphs you'll see on exams, or like maybe on like a programming assignment. Usually we don't allow self loops. It doesn't really break much. In terms of like some algorithms, it might be a little bit more confusing, but not really for the ones that we use. But there just happens to not be one here. Okay, and the rest would be false. So this would be false, that'd be false, that'd be false. It's gonna get a little messy if I write all the falses, so I'm just gonna only write the trues. And if something's blank, just assume it's false. Okay, B again is adjacent to just D. And actually we can use our adjacency list to fill in the rest. We don't need the graph, right? Because they're both the same representation, they both contain the same information. Okay, so B has an edge to D, so B to D is true. C has no outgoing edges, so the whole row of C is going to be all falses, or in this case, all blanks. D has an edge to C and to E, so D has an edge to C and to E. And E has no edges, no outgoing edges, so it's all false. And F has one outgoing edge to E. Okay, so you'll notice that this matrix is pretty sparse, meaning there's not that many true values. There's only 7 out of a possible, 6 by 6? Yeah, 7 out of a possible 36. So it's only like 1/6 the way full you can think of. And so no matter, how many edges there are on your graph, this adjacency matrix would always have space theta of n squared, where n is the number of vertices or nodes. And that makes sense, right? Because it's like you're keeping this grid in memory, where the grid, the number of rows and the number of columns are both n, right? Because we need to represent every possible pair of nodes or vertices. So I might interchange between the two words. Nodes and vertices, they're the same thing. Okay, so theta of n squared space, whereas the adjacency list is a little bit sparser. So if an edge doesn't exist, we don't, store anything for it. So it's going to be O of n squared, right? Because in the worst case, you actually do have every possible edge, but you might have less. And in this case, it turns out to be quite a bit less. So there's only 7 edges here, so there's only really, you can think of 7 memory we're using, whereas in the adjacency matrix, it's 36 memory. You might want to think of it as. So there are certain cases where one is better than the other. So, and it's not really in terms of, first of all, that matters only, again, with when you have large n. So if it's a really big graph, then it might actually matter, this theta of n squared might be too much. So you might want to opt for something smaller. But if the graph has a lot of edges in it, then, right, because this is O of n squared, right? So it's going to be pretty close to the theta of n squared. So if there's a lot of edges, then it doesn't really make much of a difference, whether you use the matrix or the list. So usually it's just whichever one is more convenient for whatever algorithm you want to use. We'll see so for example, traversals, one operation you'll do a lot is, from a node. So maybe just randomly I'll pick D. I want to know what are the neighbors of the node, right? So maybe this is the successors method from homework 9, or the in project 2 LOA, when we had the numcontig method. You kind of want to know the neighbors of this node or square, right? That's a pretty frequent operation. And in the adjacency matrix, what you'd have to do is you go to the row labeled D, right? Because of this row, let me mark it. So this row, and you have to go through everything on that row, and any value that's true, that's a node you should add to like a list that you make on the spot. So in this case, we'd add C and E. So even though there's only 2 edges here, 2 adjacent nodes, we'd have to go through we have to go through and kind of cross-check with first, is there an edge with A? Is there an edge with B? So it's like this theta of n runtime, sorry, theta of n complexity operation. And if you're doing that a lot, then it might be pretty slow. Whereas in the adjacency list, all you have to do is index into it with the key D, and you automatically get C and E right there, right? Even though there might be a million different nodes in the graph, this would take no time because you just index, get to the list, and then just return those two things. Whereas in the adjacency matrix, if I wanted to know if I want to know what the neighbors are or successors of a node, I have to cross check it with every possible node, and that might take a long time. So that's one example where you might want to use the list over the matrix. Yeah, I think I said enough there. Okay, so yeah, it should look like this. And remember, in the matrix, all the blank ones should be false. I just didn't want to get too messy. Okay, now we can do the traversals. So let's start with the preorder. So DFS preorder. One thing that you'll see as we do this is that there's going to be ties or kind of some source of like where we need to make a choice. And in general, like these two lists, like the list returned by preorder and the list returned by postorder, they're not unique. So they could have been one of many different things. And same with BFS. So all these algorithms are like when you say preorder or postorder, it's an ordering on the vertices. So it should return like a list of nodes. And in this case, if there's like a choice we need to make, which is like this last sentence here, if there's a choice of which node we need to go to, we're going to visit in alphabetical order. And we're going to see that right off the bat with preorder. Okay, let's get rid of these numbers. They don't matter anymore. And we're starting off at node A. That matters because you got to start somewhere. So starting from node A. Okay, it's pretty easy to do these like on an exam or something because you don't really need to know like the whole algorithm, and you don't need to like make a stack or anything like that. You can basically, there's like this method or this way of solving these problems where you just kind of use your finger and kind of walk through it, and it's super easy. So I'll show you how you do it. So you start off at whatever starting node. In this case, it's A, and you're gonna go through the vertices, and since it's depth first, we're gonna go right. We go like kind of as far deep as we can. So the first path might look something or will look something like this, right? And I went to B instead of F or E because that's how we break ties in this problem, right? Whenever there's a choice of which node to visit nodes in alphabetical order. So that's why from A I went to B because B comes before E or F. Okay, B does not have a choice. It has to go to D. So B goes to D, and D could have gone to E, but again, the alphabetical order dictates that it goes to C. So now we're at C, and now we're stuck. There's nowhere for C to go. In general, what I'll write is, stop. So the stopping condition is stop when no unvisited, or let's say unmarked neighbors. And we're going to mark something when we're all done with it. So basically, you're going to mark something when all of its neighbors are marked. Or maybe let's call them successors, because neighbors kind of has this, like maybe you think D is a neighbor of E, but it's not. And I think successors makes more sense because it's directed. So E is a successor of D, but D is not a successor of E, right? Because of the arrow. Okay, so stop when no unmarked neighbors. Well, C has no neighbors at all, right? So it satisfies that condition because it has no neighbors. So you can also say none of its neighbors are marked. I wrote this condition wrong. Stop when no unmarked neighbors, or maybe let's write it and maybe a little clearer. Stop when. This is gonna be the same thing, but maybe a little clearer. All neighbors are marked. Actually, let's do this. Okay, the same thing as I wrote before, but like the negated version or the whatever it's called. So stop when all neighbors are marked. Well, C has no neighbors Or sorry, I said successors. Let's do successors. All. Okay, so stop when all your successors are marked. So C has no successors, so it does satisfy the stopping condition because all of it, like, it has no successors, so it just, like, I think what they say is like vocatiously true, because there's no successors to B marked or unmarked. So C's done, right? C's marked. So let's mark it. In this case, I'll just put a star like next to it so you can still kind of see the node name. So C's marked. And we're gonna exit it. And as we're doing, okay, actually, let's start with post order. Sorry, kind of a little all over the place. But okay, so yeah, the finger thing, right? So our finger, this red kind of line represents what our finger's doing. So in post order, when we leave a node, like when we mark it, right? That's when we leave it. That's when you write it down in the list. So you'll append it to your list. Right now our list is empty. So we're going to append it, C, right? Because we left it. So that red thing, that red mark is our finger exiting C. Okay, so now we go to D. And D is not marked. D has successors that are unmarked. In this case, E, right? E has not been marked. So we're going to go to E. And we're entering E, so we're inside E. And E does not have any neighbors, just like C. So it's in the same boat where it's like vocatiously true. So I'm going to mark E, and I'm also going to put it in our list here. Okay, C and E. So those are the two ones we visited, and those are the two marked ones. Okay, back to our finger. We exit E, right? Because when we exit E, when we exit a node, that's when we put it in our list. And now we go back to D, and D has all of D's successors are marked, right? C is marked, and E is marked. So we're going to mark D, and we're going to move our finger along, and we're going to exit D. So we exited D, and we exited it, so we need to go to our list here and add D here. And now we go back to B, and B has one successor. It was D, and it's marked, so B gets marked. And we add it to our list. And our finger goes back to A, and it doesn't go back to E because E is already marked, but it does go to F because F's unmarked. So we're going to go to F, and F has no neighbors. F has no successors. Or F does have a successor, but it's marked, right? E is marked. So it gets marked. We're going to write F there, and F's all done, so it goes back to A, and all of A's successors are marked, right? B is marked, E is marked, F is marked, so the algorithm just stops here. So A gets marked, and we add it here. And that's it. So that's our post order. The pre-order is it's the same thing, maybe a little bit easier because it's not when we exit a node that we write it down, but it's when we enter a node that we write it down. So we're going to do the same exact path, except now we're just going to add to our pre-order list when we enter the node. So let's, and it's the same condition here, the stop when all successors are marked. Because we're still I like to think of it as like DFS is like the vehicle of which we're traversing the graph, and then whether it's pre-order or post-order, that's when we, depending on which one it is, we will add to our list at different points of the algorithm. And there's not really like a clean relation between the two. Like it's not like the post-order is just like the reverse of the pre-order. It's nothing like that. Maybe for like a special graph it might be, but not in general. Okay, so we're gonna do the same thing, right? We start at A. So let's trace out with our finger what we're gonna do, because we already kind of know what's gonna happen, right? Because from A, enter B, go to C, enter C, exit C, D still is unvisited, enter E, exit, D's all done, it goes back to B, A says, oh, F is unvisited, it goes to F, and then it terminates like that. So what happened there? First, we entered B, right? So B is the first thing we entered. So B is added here. Okay, so we entered B. Then we went to D, right? So we entered D. Oh, we totally forgot. We entered A before all of these. A. Yeah, so A, then B, then D. Okay, so we're at D, and now we could have gone to E, right? But because of the tie-breaking scheme, we chose to go to C. So we entered C. C got entered. And C has no marked successors, right? So like the condition, again, it's like vocaciously true. So it gets marked. And now we go back to D. And D has an unmarked child, successor. It's E. So we go inside E. And we just entered E. So we're going to add it here. And E, again, just like C, no unmarked successors. Sorry, no marked, all of C's successors are marked. Sorry, all of E's successors are marked. So visit it there. Now we're back to D, and both of D's successors are marked. So it's done. Now we go back to B, because that's where D came from. Same story, so mark it. A could still go to F, so A will go to F, and we entered F, so we add it to our list. And that's the last node, so I'll close it. So F gets marked because it has no unmarked neighbors. Then go back to A, and A is marked. So we did the exact same thing that we did from the the post order, except the only difference is when we chose to add it to our list. And it's when our finger entered the node, not when it exited finally. In terms of code, you would need a stack for this, because we could tell kind of in our when we went through this by hand where we came from. Like we knew, okay, once we're done with D, we need to go back to B. But in the code, you would need to store that like explicitly, and so that's with a stack, because it has like stacks the perfect data structure for this like recursive sort of structure where like you start at A and then you go to B and then you basically restart the algorithm from B. And once you're done there, you go to A. You go back to A. So you can either do this iteratively with a stack, or you can use an implicit stack where you use recursion. Because recursion, like if you might remember from like 61A, you have like the frames. You'll have F1 and then like F2, or I guess in terms of like, I forgot the diagram name. Like yeah, I don't know what the diagram names are, but like the frames that go like this, right? F3. And then when you're done with like the third frame, you kind of pop back into the second one, pop back into the first one. So it's like a stack there. Okay. So those are the pre-order and the post-order. So note that it's not like I said earlier, you can't just like reverse one to get the other. Like if I reverse this, I don't get post-order. There's not really a clean relationship there. Let's see. Oh, and also they're not unique. They will be unique if you mandate a tie-breaking scheme, in our case alphabetical order, then it'll be unique. But if there's no tie-breaking scheme, then there could be a bunch of different pre/post valid pre-orders / valid post-orders, because like maybe we chose to visit F before B, then we get a different post/pre-order. Okay, now let's do BFS. And BFS doesn't have a post/pre-order because we don't go depth first. Like well, I guess that's kind of obvious. We don't go depth first. We'll see as we like write that why it wouldn't really make sense. Okay, in this case, I actually will use a queue or like a data structure because just to keep track of things. So you can't really do this with your finger because you need like to like spread out and kind of be at multiple nodes at the same time. So we start at A. So I'll mark it. I'll stick with the red. So I'll use the red to denote where our queue is, and I'll also write it too. So our queue. Let's actually do this. That's probably how you spell it. So just A right now, right? Because that's where we start. And now we add things to the queue, right? And then what kind of... Yeah, and it's BFS, right? So when you add something to the queue, or actually, we'll say when you pop something off from the queue, that's when you like visit it. So we start at A. So our queue is initially just A, right? So your iteration, you need to pop off the queue. So the only thing to pop off is just A. So that's what is done here. So A. So A gets popped off the queue, and it's like the node in question is A, or maybe like the current node. It's probably better. I'll just call it cur. So the current node is A. Okay, so it's no longer on the queue, so it's not red. I'll circle in black. So it's the current node is A. So now we need to add all the successors of A, and we'll add them in alphabetical order because that's what the instructions say, right? If there's a choice, put it in alphabetical order. So first we'll add B, then we'll add E, then we'll add F, and we add all of them at the same time. Okay, erase that stuff. Let's mark our Q. Our Q is B, E, and F. And one thing you'll note about the queue is the nodes in the queue, at least at this stage, they're all the same distance from the start node. In this case, our start node was A. The one kind of weird case here is E, because you could say E is like distance 1, right? Because it's one node here, but you might also call it distance 2 because you can do that. Here the distance is just like the smallest distance. We'll see later on that it doesn't need to be all the nodes in the queue are not the same distance, but there can be a max of like one difference between them. I think there's a question on last week's discussion, or maybe this week's exam prep discussion, where you can like see a formal like argument for that. But I'll just say it here and leave it at that. Okay, so that's the queue. Now let's pop off the queue. B gets popped off. So let's mark it in red, and I popped it off, so I will add it here. And now let's add B successors to the queue. I'm going to scoot these up. B successor is only D. So just D, and it gets red because it's in the queue. And that's it. Okay, so B's done with. Now it's E's turn. We pop E off the queue. And I popped it off, so I will add it here. Okay, what is E adjacent to? Let's get rid of that. It's the node in question. E has no successors, so nothing gets added here. So the queue stays the same. I'm just going to move them up. That's it for E. Now it's F's turn. F is the current node. We do that. Okay, F has... Okay, another thing I should have done is when you pop off a node, you got to mark it, just like in the DFS case. Because otherwise, then there's nothing stopping me from trying to add E again here, right? Does that kind of make sense why? Because if you didn't mark it, how would you know to not add it again? So you would need like an external, like visited set, seen set, to make sure you don't go to the same node twice. And so that's just like a quick if condition. You can either say like, you could have duplicates in your queue. So maybe for whatever reason you have duplicates in your queue. That's okay, as long as when you pop off here, first, before you add the successors, you just check, okay, is this node in the seen set? And if it is, oops, then you should just go to the next one. Or you could also have it where you have like this invariant that your queue is only nodes you have not visited before. So it's no duplicates. Both of those are totally fine. So you can kind of move that if condition with the scene set. You can move it around, whether you want it to be applied to the current node or whether you want it to be applied to the successors. It doesn't matter. Okay. But yeah, in this case, we'll just like keep in mind like our heads, which ones we've seen before. Okay. So we're at F and we don't add E because we visited. Yeah, I think we visited E. Yeah, we already did E, so we're not going to do it. But we do need to add F here. Yeah, we don't add E because remember we've already visited it. So we're done with it. It's now D's turn. So it's D's turn. And yeah, so we popped D off. So did we not? Yeah, no, that's right. That's right. D. And D has an unvisited neighbor C, so we'll add that here to the queue and mark it in red because it's in the queue, like, or fringe if you want to call it. And D's turn's over. Now it's C's turn, so C goes here. Oops. And C has nothing. Well, first we need to add C here. And C has no outgoing edges, so nothing is added to the queue. The queue's empty, so we just stop. And so, like I said earlier, this ordering here is related to the distance of that node from the start node. So let's write those distances here. So A is distance 0 from itself. B is a distance 1. E is a distance 1. Even though E can be reached via two edges, we say it's like the minimum. So 1. F is 1. D is 2, right? Because you go from A to B to D. And C is 3. So if you notice, you'll see that we these are kind of sorted in order, like increasing order in terms of distance from the start node, where the start node is included, right? Just 0 distance from itself. So I think this is on one of either this week's exam prep or maybe last week's, but there's a cool like sorting algorithm if you want to do Dijkstra's in a graph where all the edge weights are the same. So either all the edge weights are 1 or all the edge weights are 10 or 1,000. It doesn't matter what the number is, as long as it's positive and it's all the same. Then you can use BFS to sort them in order from least to greatest, right? Closest to furthest. And that's because of the way we pop off the queue and add to the queue, and the fact that it's a queue and not a stack. Okay, that was pretty long, but I hope that clarifies some things about BFS and DFS, and maybe the pre-orders, and maybe like some more nuanced things between them. Like, can I just reverse this thing and get the post order? And the answer is no. Okay, so topological sorting is, if you remember from lecture, one thing it's used for, or like the main thing it's used for, is like dependency, anything sort of with dependencies. So if you want to topologically sort a graph, so first of all, a topological sort of a graph is an order of the nodes or vertices, such that, let's say, like you can't, like, for example, if BA, like, the order was something 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 B, then A, and then something something something. That's not a valid topological sort, because you can only go to B after you've gone to A, because this edge kind of denotes like there's a dependency there. Like you can't, like, from A, then you could go to B or E or F, but you can't really do one without the other. So I like to think, like, the easiest analogy is like classes. So this is convenient. I can just do 61A, 61B, 61C, and so on. Or I don't think you need 61B for 61C, but maybe I'm wrong. But in this, like, if these three are the only nodes in the graph, so just ignoring these for now, this means that you cannot take 61B until you've taken 61A, because there's a directed edge there, right, with an arrow like that. And the same thing for 61C. You can't take 61C until you take 61A. And you can have more complicated things, like for example, E here. E you can't do, E is kind of actually trivial, because you can, if you've done this thing, you've definitely done this thing, right? Because there's an edge there. So this edge kind of doesn't really do much. But maybe you can have something kind of more interesting, like if there was an edge here. Then in order to take whatever this class is, whatever class E is, you need to take 61B and 61C, which implies you've taken 61A because you've taken both of those. So this edge, again, not really doing much. Okay, so that's what a topological sort is. It's like an ordering on the vertices. So you can think of that ordering in terms of the classes. Like, you can take the classes in this order, and you won't have any prerequisite errors, or I don't know what you want to call it. Okay, yeah, let's get rid of this stuff. And one way to figure out a topological sort that you might remember from lecture is you just take a DFS post order of the graph and reverse that. So the post order here, and just reverse it. Yeah, I'll write it out. So A, F, B, D, E, and then C. Okay, so let's see, is that actually valid? Okay, so this is saying I can take the classes in this order. Let's see. Oops. Okay, so I'll take class A, and that will allow me to take class F. Okay, so that's true. Then it says, okay, take class B, and I can take class B because I've already taken class A. Now take class D, and that's allowed because I've already taken class B. Now take class E, and that's okay because I've taken class F and A, and then class C, which is allowed because I've taken class D. Okay, so that is valid. That's a good topological sort of the class, the vertices. Now the reasoning why a reverse DFS post order makes sense is the following. So let's say the post order was like, let's say it was wrong. So in the topological sort, maybe the wrong thing is like B and then A. So something, 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 B, A, something, something, something. That means in the the post order, you had something, 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 A, then B, then something, something, something. And remember, in the post order, we added something to like this list only after our finger exited it. And our finger exits it after we've visited all of the successors. So this, if we had this A and then B, that means that we visited all the successors. Sorry, we visit A before we visit B, but that cannot be because there's an edge here, right? So we wouldn't even be able to visit A until B is visited and E and F. So that's obviously not like a formal argument, but I hope it kind of makes sense where it's like there is this issue of dependency in the post order where you can't visit a node until you've visited all of its children, which is like the opposite of what you want for topological sorting. We want the opposite. You can't visit these children until you've visited the current, like the node that has the edge to all of them. So that's why you need to reverse it. It's okay if you can't like write like a formal proof. I probably couldn't either on like why it's like why this is valid in all cases. Like there might be like some weird case that you might have to argue for. But if you get a gist for it, or hopefully you do get like a gist of it from this. Like there's like in the DFS post order, there's this concept. This is like this idea of dependency kind of baked in from the fact that there's like it's like recursive because there's like a stack, and the stack has like this. You can think of like what's the word? There's like this ordering on top of it when you have a stack because like of the different frames, like I said earlier. Okay, that wasn't really that clear. So as long as you know that it's like reverse DFS post order, that phrase, that's basically all you need to know. Okay, there's a valid topological ordering. Is it unique? No, because the DFS post order is not unique, right? No. So in this case, like it's definitely not unique because after I take class A, I could either take class B, directly next, or I could take class F, or I could take class E. It doesn't matter. So there's nothing unique about a topological sort, unless it looks like, A and then B, C, like linearly like this. Maybe D. Actually, no, even then that would not be unique. So like if it's like linear like that, then yes, it's unique, but not in general, no. Okay, and also note that you can't have a topological sort if you have a cycle. So if I add something like this, A, B, C, back to A, that doesn't make any sense because that means like to take class A, to take class C, you need to take class B, right? Because there's an arrow from B to C. Okay, so if I want to take class C, I got to take class B. To take class B, I need to take class A. So to take class C, I need to take class A first. But to take class A, you need to take class C. So undoing all of that, like all those implications, to take class C, you need to take class C. So that doesn't make any sense. Like the class is its own prerequisite. So there's no way to take that class. So there's no valid order to take these classes at all because there's a cycle here, right? A, B, C, A, B, C. So if you have a cycle like that, then there's no topological sort. It wouldn't make sense in that graph. Okay,